Okay, in this video we'll be going through the 2016 Mechanics Exam. Alice is in a car on a ride at a theme park. The car travels along a circular track that is banked as shown in the diagram. Draw labeled vectors to show the two forces acting on the car. You can assume there is no friction. Okay, so the two forces that are acting on the car, the first one being is obviously the weight force, right? And we know that the cart is not going straight through the ground, therefore there must be a reaction force, aka a normal force, acting perpendicular to the surface, and so we know there is a normal force acting up this way. And for accuracy purposes, this normal force needs to be much bigger than the weight force. There we go. Now, some people might say that there are three forces acting on it. There's the centripetal force, right? However, this is not the case because the centripetal force is not a force acting on itself. The centripetal force is provided by another force. And in this case, the centripetal force is provided by the horizontal component of the normal force. So Fnx, we can call that horizontal component. And that is the reason why the normal force has to be greater than the weight force, because not only is the normal force providing the centripetal force, but the vertical component of the normal force is equal to the weight force. And so, because it's both providing the centripetal force and acting in direct opposition to the weight force, the normal force has to be greater. But you don't need that for your answer, that's just some theory, so you understand. The mass of the car and its passengers is 960 kgs. The track is banked at an angle of 20 degrees. Use a vector diagram to calculate the size of the centripetal force. Okay, so if we remember our vector diagram, we have a normal force coming up this way. Then we also have the weight force acting downwards. And so if we draw that out, we have our weight force like so, and then we have our normal force acting here. So this is our weight force, this is our normal force. And as you can see, there is a net centripetal force acting that way. Now this right here is our 20-degree angle. I often get asked, how do I know that that is 20 degrees? The reason why I know that is 20 degrees is if I just draw out our situation again. This is our 20-degree banked angle, and we have a car over here. We have our normal force acting over this way, and then we have our weight force. You can imagine if I reduce this angle, the normal force will move upwards, correct? If this angle is now only 10 degrees, so I've reduced the angle, the normal force will act slightly more vertical, 10 degrees more vertical to be exact. And so as you can see, the steeper the angle, the more horizontal the normal force is going to be. And the lower the angle, the more vertical the normal force is going to be. And so if we look at our vector diagram, if we reduce this angle, let's draw it with a reduced angle, like so. This is now 10 degrees. You can see that the normal force is now more horizontal. Whereas if I increase the angle to, let's say, 30 degrees now, and that is our centripetal force, you can see this exaggerated diagram that the normal force is much more horizontal. And so that is how I know that that angle right there is the angle of the banked corner, rather than this angle right here. And so what do we know? We don't know the normal force of the car, but we do know the weight force, because we have the mass, and we also know the acceleration due to gravity is just 9.81. So we know our weight force is equal to mg, which is equal to 960 kgs times 9.81, which gives us a weight force of 9,417.6 newtons. We can see that we have the adjacent side, and we're trying to find the opposite side of that right angle triangle, and so we can use our tan theta relationship, and therefore our tan theta is equal to the centripetal force all over the weight force, and therefore tan 20 degrees is equal to Fc all over 9,417.6, and therefore 9,417.6 times tan 20 degrees is equal to our Fc, and that gives us a centripetal force of 3,430 newtons. There we go. The following diagram shows a part of the roller coaster track with the car at two positions. Compare the forces that the track exerts on the car when the car is at the top of the hill at position A, with the forces that the track exerts on the car when the car is at the bottom of the hill, which is position B. Okay, so at position A, we know the cart has a weight force, as usual, and therefore again, as the cart is not just going directly through the track, it's on the track itself, there has to be a normal force acting directly upwards that is equal to the weight force. And this normal force is provided by the track. So the track provides a normal force that is equal to the weight force. Now at position B, again, we still have a weight force acting downwards, and there still is going to be a normal force. However, in position B, the car is now moving in a vertical circle. Now, because of this, there has to be a centripetal force provided. We know the centripetal force always acts towards the center of the circle, so it's acting in this direction. And the only force that is acting in that direction is the normal force. And therefore, the normal force also has to provide the centripetal force, and therefore, the normal force is going to be greater than the weight force. I didn't draw that much bigger. Has to be greater than the weight force. There we go. Noticeably larger. And so you can write that explanation in yourself. At the top of the circular loop, the force that the track exerts on the car is 0. Using energy considerations, calculate the height of the hill if the radius of the loop is 5 meters. You can assume there is no friction. Okay, so if you watch my video on vertical circles, you know that if the track exerts 0 force on the cart, that we are now talking about the minimum speed. We also know that this is a conservation of energy question because it says using energy considerations. That's talking about conservation of energy. So if we just redraw this situation, we have a hill right here, and then we have the loop coming down like this. That is horrible. That is slightly better. Okay. So we have this radius, which is 5 meters, right? And we're trying to find the height of this hill. So using energy considerations, we know that the energy at the top, the gravitational potential energy, has to equal to the gravitational potential energy at this point plus the kinetic energy that we have at that point because the car is now moving. And so mg big H, right, that is the height, is equal to half mv squared plus mg2r. The reason why I say 2r, because that is twice the radius, right? This height right here is 5 meters plus 5 meters, so 2 times the radius. Now, because we have masses on both sides, we can divide by the mass on both sides, and those just cancel out. And we're left with gh is equal to half v squared plus g2r. Okay, so now we get to this point right here. We know our g, because g is just 9.81. Our height is what we're trying to find, so it's reasonable that we don't know that. We know our radius, which is just 5 meters, so 2 times the radius is just 10. However, we do not know our v squared. The clue is that we're talking about minimum speed, and if you've watched my vertical circles video, you would know that at the minimum speed, the centripetal force is entirely provided by the weight force. And so we know that the centripetal force is mv squared over r, and that's equal to the weight force, which is just mg. Again, because we have masses on both sides, we can divide by mass on both sides, and this cancels out, and we get v squared over r is equal to g. And therefore, v squared is equal to gr. Now, usually I would square root both sides. However, in this case, we just want v squared, and we already have v squared, so there's no need to square root both sides. And so, therefore, v squared is equal to 9.81 times r, which is just our radius, and so that's times by 5. And therefore, v squared is 49.05 meters per second. So now bringing this down here so we have more room for working, we can now plug in our numbers. So we know that 9.81 times by h is equal to half v squared, which we know is 49.05, plus 9.81 times 2r, which is just 10. Right? Alright, so now that we just want h on this side, we don't want 9.81h, we can divide both sides by 9.81, and we get h is equal to half 49.05 plus 9.81 times 10, all over 9.81. And therefore, putting this in our calculator, this gives us a height of 12.5 meters. There we go. Okay, question 2. A solid cylinder and a hollow cylinder of the same shape and mass are rolled down the slope. State the energy changes that take place as the cylinders roll down the slope. Okay, so when they are at the top of the slope, this is when they have the most gravitational potential energy, right? They are not moving as well, so they have zero kinetic energy. And you can imagine when they are at the bottom of the slope, this is when they're going to have the least gravitational potential energy and the most amount of EK. One thing that you have to take into consideration is that these are cylinders, and therefore when they go down the slope, they're going to roll. The reason why this cannot be ignored is because in the question, it says we can ignore heat and sound, however, we cannot ignore friction. So friction is what makes things roll, and so therefore there is going to be rotational kinetic energy as well. So both cylinders are going to have gravitational potential energy at the top, and as they go downwards, that gravitational potential energy is going to convert into linear kinetic energy and rotational kinetic energy. The hollow cylinder has a radius of 0.058 meters. It rolls down the slope and reaches a speed of 0.25 meters per second at the bottom. The rotational inertia of the hollow cylinder is 0.14. Calculate the rotational kinetic energy of the hollow cylinder at the bottom of the slope. Okay, so if we have the hollow cylinder, because this is the hollow cylinder, we can assume that the mass is entirely on the border, and so the effective radius is just the radius of the cylinder. And because we know that omega is equal to V over R, we know it reaches a speed of 0.25 meters per second, and that's all over the radius, which is 0.058. And that gives us an angular velocity of 4.31 radians per second. There you go. Now we know that rotational kinetic energy is equal to half I omega squared, right? And so therefore half I, which is 0.140, times omega squared, which is 4.31 squared, and that gives us a rotational kinetic energy of 1.30 joules. There we go. The hollow cylinder starts from rest and has an angular acceleration of 1.72 radians per second. Calculate the time it takes to complete one full rotation. So we know that our theta is equal to omega I t plus half alpha t squared, right? Now we know that our omega I is just the angular velocity in the beginning, and we know that is 0. And so therefore this term can cancel out, and therefore our theta is equal to half alpha t squared. Now we know that one full rotation is just 2 pi, right? So our theta is 2 pi. Our alpha is just our angular acceleration, which we're given as 1.72, right? And the t squared is what we're trying to find. And so rearranging for t, we get 2 theta all over our alpha is equal to t squared, and we can simplify that to t is equal to the square root of all of that. And so now plugging in our numbers, we have 2 times 2 pi, which is just 4 pi, right? All over 1.72, which is our alpha, and this gives us a time of 2.7 seconds. There we go. The solid and hollow cylinders are both released at the same time from the top of the slope. Explain why the solid cylinder reaches the bottom of the slope first. Okay, so for the solid cylinder, so CS, solid cylinder, because it is solid, as I is directly proportional to mr squared, its effective radius is going to be less than the hollow cylinder, right? Because more of the mass is closer to the axis of rotation, and therefore for the solid cylinder, its rotational inertia is going to be less than that of the hollow cylinder. Now, because we know our rotational kinetic energy is equal to half I omega squared, because I is decreasing, it's going to have a lower amount of rotational kinetic energy, and therefore it's going to have a higher amount of linear kinetic energy. The reason for that is because both the hollow and solid cylinders start with the exact same gravitational potential energy, and therefore, because the solid cylinder has less rotational kinetic energy, it must have more linear kinetic energy than the hollow cylinder. And therefore, as it has more linear kinetic energy, if we look at our slope, because linear kinetic energy is the one that's actually making it go down the slope, because it has more of that, it's going to go down the slope faster than the hollow cylinder. And so you can write that in beautiful words. A toy bumblebee hangs on a spring suspended from a ceiling in the laboratory. Tom pulls the bumblebee down by 10 centimeters below the equilibrium position and then releases it. The bumblebee moves in simple harmonic motion. State the 2 conditions necessary for simple harmonic motion. Okay, so the restoring force is proportional and opposite to the displacement. There we go. You finally have me writing stuff down. You'll see this question come up a lot. Okay, I'm pretty sure this was also in my exam as well. So This is a very common question, very easy achieved mark. The bumblebee's oscillation has a period of 1.57 seconds. Calculate the bumblebee's acceleration at time 0.25 seconds after Tom has released the bumblebee from its lowest point. Okay, so we're looking at acceleration right now, obviously, because that's what it says in the question, and we're also looking at simple harmonic motion. Now, if you look at your formula sheet, our acceleration in simple harmonic motion is given as negative a omega squared cos theta, right? Or cos omega t, because theta is equal to omega t. The reason why we know it's this one and not this one, right, is because we start not at the equilibrium position, but at max displacement. So if we start at max displacement, we get this equation right here. So we know our amplitude, which is just 0.10 meters, right, because that's the same thing as 10 centimeters. We know our time, because our time that's given to us is 0.25 seconds. Now we just don't know our omega. We do know that omega is equal to 2 pi over t, right? So we know that omega is 2 pi over t, so that's 2 pi all over our period, which is given as 1.57, which is given as 4 radians per second. There we go. So now that we know that, we can just simply plug in all our numbers. We get our acceleration is equal to negative 0.10 omega squared, which is just 4 squared cos 4 times 0.25, which is just 1, right? So our acceleration is equal to negative 0.864 meters per second per second. There we go. Also, make sure your calculator is in radians, because I just spent the last 5 minutes wondering why I keep getting the answer wrong. No, it's in radians. I mean, I was in degrees, not radians. Tom pushes the bumblebee with a very small force at regular intervals of time, so that it eventually is moving up and down at very large amplitudes. State the name of this phenomenon and explain how the bumblebee's motion develops a very large amplitude. Okay, so this is a basic example of resonance. Right, resonance is basically when we add energy, aka pushing the toy, into the simple harmonic motion system at its natural frequency, right? And this will cause the amplitude to increase. The example that I always use for this for my students is that if we have a child on a swing, how do I draw a child on a swing? Child on what is okay? Child is on a swing. All right, you get the idea. Okay, and this child is swinging, right? It's swinging back and forth. We know that if we were to stand over here, right, and we are going to push this child, we know that we should push the child as it comes that way, right? We know that we should push the child when the child is roughly here and it's about to swing this way. We shouldn't push the child when it's coming towards us, right? If we push it as it's coming towards us, that's just going to put the entire system to a halt, right? So we should push the child over here. That is at its natural frequency. So in the case for this, pushing it at its natural frequency would mean that if we have the bumblebee on a string, this circle is a bumblebee, just imagine. I can probably put more effort into that. That's like a bumblebee, like you get the idea. Okay, so that's our bumblebee, right? The bumblebee is going to move up and down. The best time to push it would probably be when the bumblebee is right here. So it's already moving down, but it's not quite at the end position, but it's moving down, and we push it just before it reaches this bottom part right here. So basically what you need to write down is that this is a phenomenon called resonance, where we add energy at the natural frequency of the simple harmonic motion system, therefore increasing the amplitude. Tom stops pushing the bumblebee when its displacement is 20 centimeters. Using the axis below, draw a graph of displacement against time for 3 complete oscillations, starting from y is equal to plus 20 centimeters. Okay, so because he has stopped pushing the bumblebee, this is going to be an example of damping, right? Because energy is now being lost to heat and friction and all that jazz. So if we draw our axis, this is going to be displacement in centimeters, and this is going to be a 20 centimeters right here. This is going to be negative 20 centimeters. This is obviously 0. We want 3 oscillations, so we have 1, 2, 3, 4, 5, 6, 7. So we can draw it as this is 1 period, 2 period, and 3 periods right here, where our time is equal to 1.57 seconds. So that's T1, 2T, and then 3T, right? This diagram is like ultra hard. They usually give you a grid, so it's like easy to place. But essentially the idea is that when we go to here, this point right here needs to be slightly above this 20, because as the bumblebee moves from here to here, it's going to lose energy, and therefore it can't go all the way to 20. It has to be slightly above it, like right here. Okay? And then once it gets back up here, it needs to be slightly below that. So if this was like 18 centimeters, this now needs to be 16, right? And so it decreases every time. So if you go to 18, now because that was at 18, we can go to like negative 14. And now that can be like 12. That can be like 10. So it's supposed to go down like that kind of graph. They usually give you a grid, so it's very easy to see it. But in this one, they didn't, so it's hard to do. But essentially, it needs to make that shape. See how it kind of goes like that. That's what you need to do. And yeah, and with that, we're done.